It is estimated that by 2050 there will be 3.6 million people in the United States living with limb loss. This number is dwarfed by the 25 million people who will also need prosthetic/orthotic devices in developing regions such as Asia, Africa, and Latin America. The number of amputees worldwide is on the rise, and technology has not kept up with the times. Currently, the industry standard is non-compliant sockets, made out of rigid materials such as carbon fiber, fiberglass, or polypropylene. While these materials are great at supporting the user's residual limb, and thus body, they cause unnatural movements when designed incorrectly, and, due to the non-compliance, may also lead to bad pressure distribution, especially when the residual limb volume changes over time. This leads to general discomfort at a minimum, and may result in chafing, tissue damage, and further edema, which creates a cycle of further damage. Compliant mechanisms, while still young as a field of research, are becoming more and more promising with the advancement of rapid prototyping and manufacturing methods, such as selectively laser-sintered 3D printing and advancement in materials such as PA2200, also known as polyamide 12. This presents an opportunity to investigate integrating the growing field of research into compliant mechanisms into the development of prosthetics. By utilizing the compliant nature of these mechanisms, it may be possible to design a more comfortable prosthetic that can adapt to the user rather than the user being forced to adapt to a rigid prosthetic socket. And, through the application of SLS 3D printing, it may be possible to produce custom and rapid solutions designed specifically for each individual, saving both time and cost. Initially, we set out to design a compliant prosthetic socket. However, we soon encountered a lack of component libraries or systematic frameworks for designing and testing compliant mechanisms. This shifted our approach to one of creating a process by which compliant mechanisms can be categorized, designed, and tested. We then attempted to verify this method by going through the process of designing a compliant socket with promising results. With a classification method and design framework for compliant mechanisms, we have created a standard approach for the otherwise open-ended and intuitive process of designing compliant mechanisms. This framework is also then compatible with a testing procedure to validate the corresponding classifications of compliant mechanisms, and allow for the optimization of implementations in parts such as a compliant prosthetic socket. It was found that the time and effort required to produce a working design was greatly reduced. However, we also found that a passive socket designed to accommodate for changes in residual limb volumes cannot differentiate between external and internal pressures. Therefore, it is infeasible to create a completely passive compliant mechanism-based socket. There is potential for active compliance to achieve a functional prosthetic socket, and we use these conclusions to help facilitate the future development of this much-needed sector.